It's been a while since I did an IMO problem on the channel, so here's one for you from 1963. Our goal is to prove that cos of pi over 7 minus cos of 2 pi over 7 plus cos of 3 pi over 7 is a half. And actually, for an IMO problem, this isn't too bad a solution. Hopefully one which is relatively approachable. Let's dive in. What are we going to start by doing? Well, it's going to be a pretty standard start. We're going to consider a function f of z, which is z to the 7 minus 1. So if you've seen complex numbers before, or maybe Vieta's formula or formulae, this may ring a bell. If not, well, you're in for a treat. So we're going to consider this function z to the 7 minus 1. And from complex numbers, we know what the solutions or the roots of this function are. It's the roots of unity. So the solutions of this are z equals e to the 2n pi I over 7, where n is any integer from the set 0, 1, 2, all the way up to 6. So it has 7 roots in the complex plane. Okie dokie, cool. Well, what are each of these roots? Well, each of these roots are just cos of 2n pi over 7 plus I sine 2n pi over 7, like so. Amazing. Okay, so far all we've done is we've defined a function f and said what its roots are. Okay, where can we go from here? Well, we're going to make an observation using Vieta's formula. So any polynomial can be factored into its linear factor. So z minus the first root, so z naught, z minus z1, z minus z2, and so on, all the way up to z minus z6. So this guy has 7 roots in the complex plane. They're all distinct. They are the roots of unity. And so we can factor it like this, where z naught is e to the 2 times 0 pi I over 7. Z1 is e to the 2 pi I over 7, and so on. Okay, and now in theory, we could expand this. I'm not going to, but I'm going to just partially expand it. Of course, if I expanded it, I get not z to the n, z to the 7 as the biggest degree of z. And then what would I get for my power of z to the 6? Well, I need to ask myself, well, how could I get z to the 6 if I expand this? Well, the only way of doing that is choosing z's from all of the brackets except one. So if I choose z from the first 6 brackets and then from the 7th bracket, I choose minus z to the minus z6, that's going to give me minus z6 in here. If I choose this z, this z, this z, and so on, but in the penultimate bracket, z minus z5, I choose the z5, and then I choose the z in the last bracket, that's going to give me minus z5. And so on, you can see that I'm going to get minus all of these z's all the way up to minus z0. So I'll squeeze that in there. So just to go over that again, I'm looking at the coefficient of z to the 6 when I expand this degree 7 polynomial. And we know the only way to get z to the 6 is from out of the 7 brackets, from 6 of them, just choosing the z term. And from the remaining bracket, I have to choose the z6 or the z5 or whatever it is. And that's how I get this term. So it's going to be whatever the negative sums of these roots are, multiplied by z to the 6. And then I'm going to have a z to the 5 term, a z to the 4 term, and so on, all the way down to the constant term. And in fact, we know that the constant term here will be minus 1 because of this up here. So f of z is supposedly identical to this guy here. So in fact, the coefficient of z here would be 0 because there's no z term up here. But similarly, the coefficient of z to the 6 would also be 0 because there's no z to the 6 term up here. And so from this, we can conclude that z6 plus z5 and so on, all the way down to z1 at z0, this must equal 0. And now we're going somewhere. We have that the sum of these guys from n equals 0 to 6, so the sum of all these roots, must equal 0. And so in particular, we can just focus on the real parts of all of these. I can ignore the imaginary parts. The imaginary parts do indeed add to 0, but I'm not interested in them because they have signs in, and this question is all to do with causes. So let's just take the real parts and just focus on adding up the causes. So we have the sum of the first 7 terms, or from n is 0 to 6, of cos 2n pi over 7 is 0. Well, let's just write out what those terms are. When n is 0, what do we get? Well, we get cos of 2 times 0 pi over 7. So cos of 0, which we know is 1. Okay, what about when n is 1? Well, we get cos of 2 pi over 7. When n is 2, we get cos of 4 pi over 7. In fact, I may stop writing cos, I might just write c. Then you get 6 pi over 7 for n is 3, 8 pi over 7 for n is 4, 10 pi over 7 for 5, and finally 12 pi over 7 for n is 6. Okay, and we know that this is all equal to 0. Where can we go from here? Well, all of these guys here, are the input of the cos function is slightly bigger than pi. So we can make them slightly less than pi by kind of reflecting them about pi. So we're going to recall the identity that cos of pi plus theta is the same as minus cos of pi. In fact, I can just say it's equal to cos of pi minus theta. And you might ask, well, why is this true? Well, we can just use symmetry. We look at a graph of cos. Pi is about here. So if you go theta to the left of it, that's the same as going theta to the right of it. So theta this way is the same as theta that way. The y values will be the same. Okay, so with that being said, what can I say cos 8 pi over 7 is the same as? Well, that's pi over 7 more than pi. So I can say that this is the same as cos of 6 pi over 7. Similarly, this guy is going to be the same as cos of 4 pi over 7. And this guy here is going to be the same as cos of 2 pi over 7, like so. Amazing. Okay, and now we can pair up these terms. We've got two lots of cos 2 pi over 7, two lots of cos 4 pi over 7, and two lots of cos 6 pi over 7. So if I bring the 1 onto the left-hand side, I have minus 1 equals two lots of cos of 2 pi over 7 plus cos of 4 pi over 7 plus cos of 6 pi over 7. Okay, now this is starting to look pretty close to what we want. If we divide by 2, so if I get rid of this 2 here and bring it onto this side, we get the half, minus half, that's fine. How do we get a cos pi over 7 out of this? Ah, well, that's something closely related to cos 6 pi over 7. We can do the exact same thing we did a second ago. We know, except maybe now with pi over 2. So cos of pi over 2 plus theta is the same as minus cos pi over 2 minus theta. So cos is kind of an odd function about pi over 2 in a way. And again, you can just look at the graph of cos and see that. Pi over 2 is this root here. If you go theta to the right of it, you've gone down some amount. By symmetry, if you go theta to the left, you go up that same amount. Hence, cos of pi over 2 plus a small amount is the same as the negative of cos of pi over 2 minus a small amount. Okay, so with that being said, what can we say about cos of 6 pi over 7? Well, that's going to be the same as minus cos of pi over 7. So 6 pi over 7 is like 2.5 pi over 7 more than a half pi. So if you subtract that from a half pi, you get pi over 7. So this is minus cos pi over 7. How about this guy? Well, this is going to be the same as minus cos 3 pi over 7. And then what about cos of 2 pi over 7? Well, that's already just cos 2 pi over 7, so that's fine. That's what we already wanted at cos 2 pi over 7. And now all I need to do is multiply through by minus 1 on both the left side and the right side. Then these two cos terms become positive. This 2 pi over 7 becomes negative, which is what we need. And then this becomes a half. And we get the goal equation, the thing that we were trying to prove. Pretty nice solution, but actually not too, if you've not seen this before, you might go, oh my gosh, how would I come up with this? But to be honest, this is a pretty well taught thing. So in high school, so maybe you're quite young, maybe you haven't done this yet, but you'll probably study this certainly in the UK and like further maths. And so this kind of way of reasoning would be pretty intuitive, something that you'd probably try when attempting this. You could also maybe try and do this by looking at double angle formulas or triple angle formulas, even maybe, and perhaps you can get somewhere. So let me know in the comments if you can think of any other ways to solve this. But yeah, a nice little IMO problem. You don't really get problems like this nowadays, but it is kind of nice to say that you've solved an IMO problem in, less than half an hour. But that being said, yeah, the ones these days are a lot more difficult, require a lot more time to get good at. Anyway, thanks so much for watching. I'll catch you in the next one. Have a great day.